welcome to our 16.3 lecture on thermochemical equations. This should be a short lecture. The 16.2 supplemental lecture covered about half of the information for this already, so as long as you watch that, you'll be good. A couple things I want to look at. First is endothermic and exothermic. I just want to go over that one more time. In an endothermic equation, you have energy or heat being added as a reactant. So it's on the reactant side, and it gives a delta H that is positive. So something like 63 joules. That positive tells you that energy was added to the reactants. Now in exothermic, that's where heat or energy is released as a product, and it has a delta H that's a negative number, so it'd be something like 236 joules, and this negative number tells you that it was released or given off. So it was taken away and given off. Now this is going to be important in this unit because whether something absorbs heat or gives it off is going to tell you what kind of reaction it is. So we need to be very mindful of our plus and minus signs in this unit. Here is an example of a thermochemical equation, actually two of them. So we have an exothermic and an endo. Notice how we have a negative sign here, so it's exo, and then this one's endothermic. So a thermochemical equation is a balanced chemical equation that includes the physical states of all reactants. So this is a physical state, this is gas, solid, all of these are physical states. So it has the physical states of all reactants and products, and the energy change, this is the energy change, usually expressed as change in enthalpy, which we know is delta H. So for this equation, this tells you that if I add iron solid plus oxygen gas, that will give me iron oxide as a solid, and it will release negative 1,625 kilojoules. So this equation, as written with the appropriate ratios, thanks to the coefficients, will give off this much energy. Now for our ammonium nitrate, breaking down into ammonia plus nitrate, that is actually going to take energy, and it's going to take 27 kilojoules to make that happen. So it's going to be endothermic. It's going to absorb that energy from its surroundings. One thing I would like to point out is if you have this equation, let's say we have our 4FeS plus 3O2 giving us 2Fe2O3. This is a negative 1625 joules. But what if I tried to decompose this? Because this is synthesis, right? We have two coming together to produce one. Well, if I decompose this and had two iron oxides breaking down into 4 iron plus 3 oxygen, we would actually have to change the signs. Even though this is a mirror image of the equation, this is a decomposition. So we're breaking this one down. And it actually requires us to put energy in. So we have to put energy in here to get this to happen. So we're going to switch the sign. So it'd be positive 1625 kilojoules. So we need to keep this in mind. We have on the next page a table of standard enthalpies of combustion. So if we are burning table sugar, so that would be sucrose plus O2 is going to give us CO2 and H2O. It's going to give off negative 5,644 kilojoules per mole. So this is 1 mole will give you that much. And as we see, the enthalpy, or heat of combustion, is the enthalpy change for completely burning of 1 mole of the substance. So this number right here is going to change based on the number of moles. So if I had half a mole of sucrose that I was burning, it's actually going to be half of this 5644. So we got to keep in mind that. And it's actually a conversion factor. So this is a conversion factor specific to each compound. But you can use it as like 1 mole gives you that much energy. And you can see we have octane, burning of glucose, propane, ethanol, methane, methanol, carbon, hydrogen. So these would all be plus oxygen, and I think most would give us CO2 and H2O. And these are all exothermic reactions because they are all negative. One other thing I'd like to point out is that standard enthalpy changes have this symbol delta H0. See this 0 right here? The 0 tells you that the reactions were carried out under standard conditions, not STP. It's actually 1 atm and 298 Kelvin. So this is standard conditions. Now STP is 1 atm and 0 degrees Celsius, or 273 Kelvin. So standard conditions, you could think of room conditions. And STP is 1 atm and 273. Alright, so calculating energy released in a reaction. So we can actually take this and have a calculation for how much something would give off. So we have how much heat is evolved when 54 grams of glucose is burned according to this reaction. So I'm going to start out with my given. I have 54 grams. Now, because this is per mole, I need to get moles. So what is our molar mass of glucose? It's actually 180 grams. So we have 180 grams in 1 mole. Okay, so this is going to give us about 0.300 moles. Now we can take that and we can use our conversion factor from this equation right here. So we have our heat of combustion. And because this is per mole, we can say 1 mole gives us negative 208 kilojoules. Now if we multiply this across, we're going to get 842 kilojoules. Now let's look at this. If we have essentially about 1/3 of a mole, it would make sense that this number would be 1 or 3 times more than what we would get here. So 1/3 of this, and this looks like about 1/3 of that value. So it's your favorite proportions, essentially. And also our number will be negative. And let's look at one more. So here we have what mass of methane must be burned in order to liberate 12,880 kilojoules of heat. So we're going to start with our given. We have 12,880 kilojoules, and we can use the reverse of our conversion factor. So we have here, they gave us for 1 mole, it's going to give off negative 891 kilojoules. So I can put that down here. And that's going to be for 1 mole. And then it's asking for methane, which we have as 1 mole equals the molar mass, which is 12 plus 4, so we're going to have 16 grams. And when we calculate that all together, we have 232 grams. And here we don't have to use the negative sign. So this negative sign here, it doesn't have to carry over to here because we're looking for grams, and grams are always going to be positive. So we can use the absolute value. And I guess that is about it for now. So thank you for watching, and I will see you in class.